Okay, so let's move on to the finite element discrete equation. So this is what we're going to do now. So far, we are in a discrete dimensional space, but that doesn't mean finite elements, right? We said that you can actually take functions that basis functions that are, they act on the whole bar, right? And that is the basis for the Rayleigh-Ritz method. So let's say you are doing dynamics and you want to get modes of vibration for a beam, for example, and then you take some Fourier series basis functions, and then you can use those basis functions in your entire bar, and it's still a finite dimensional space. You end up with a system of linear equations to solve. In fact, you end up that for dynamics you end up with an eigenvalue problem to get the eigenshapes and so on. But those functions are acting globally, and that is not what we want. Okay, what we want instead is to subdivide the bar in little elements, and what we're hoping for is that the behavior in each element, if it is very simple, it can be as simple as we want, right? But the behavior of the whole is going to approximate very well the solution, because we can actually make all those elements as small as we want, right? So any complicated function, if you try to represent by piecewise a linear function, you agree that the smaller the elements, then this function is going to become better approximated. So that is the whole idea behind finite elements. Okay. So okay. So what is the idea? Well, now we divide the bar. Into segments, which end up being called finite elements. And we use simple functions that act locally in those segments. Not globally anymore, locally. Oh. So let's see how that works. This is our bar. Yeah. And what we're going to do now, imagine that this is your, let's say, x-axis. And what we want to do is to represent functions locally. And so let's use another color. Let's go to this one. Yeah, let's say this is the value of the function, right? This is let's do it properly. And let's call these phi1, phi2, phi3, phi4, C5, A6. These are called normally hat functions. Okay, they are linear, and the maximum value of these functions is equal to 1. And they ramp down to 0 at the other nodes of the element. And we'll talk about a few properties of this approximation. So how we express our solution. So if this is, let's say, element 1, element 2, 3, 4, 5. So we subdivided the bar in 5 elements, and we choose these type of functions, linear functions. And so our trial solution is going to take the form yeah. So if you remember, these we called basis or shape functions, and these are the degrees of freedom. Well, for this particular type of basis functions, you can write them x minus xi minus 1 divided by xi minus xi minus 1 for x in the interval xi minus 1 xi, or xi plus 1 minus xi divided by xi plus 1 minus xi for x belonging to that order. So you see that these are piecewise linear shape functions. Xi plus 1. Yeah. So let's talk a little bit about these functions. They are super special, and the reason for that is that if you take a look at the node, so if you look, those are the elements, but you can think of, the ends of those elements and being the nodes. Yeah. If you take any node, let's take, for example, phi2 right here. This function. You see that this function here has a maximum value of 1. And every other function at that location has a value of 0. This is what is called a Kronecker delta property, and we'll write that in a minute. But it is nice because if the value of that function is equal to 1 there, right, then that means the degree of freedom that is associated to that function has the physical interpretation of being the displacement at that node. Okay, this is the very first nice property of the standard finite element shape functions. And I'm saying this now because later on, when we are going to more advanced formulation, this property is sometimes lost depending on the functions that you are using to enrich your finite element space, to augment your finite element space. This property is lost. And so in order to get the value of the displacement, you have to apply the whole interpolation. You cannot just look at the degree of freedom, because the degree of freedom alone is not going to tell you anything. Okay? So this is very important. The other thing that you have here is that these functions, they define what is called a partition of unity. And this is a very important concept that is going to come, in this course, is going to show up many times. So what is a partition of unity? Well, if you pick any point in that domain, right, and you sum all the functions that are non-zero there, that is equal to 1. So in a way, I'll write this down. The sum of shape functions at any point along that bar is equal to 1. This is a partition of unity. These are the two nice features that this particular set of basis functions has. So let's write it down. So shape functions are linear hat functions and satisfy phi of I evaluated at xj is equal to delta ij. So xj here is basically the location of a node. It's not a coordinate, it's the location of a node. Okay? Known as the Kronecker property. As a result, doves physically represent the displacement at the corresponding node. Also, we said that these functions form a partition of unity. And I'm going to put that in quotes because it's a very nice and very important concept that will come back later when we look at the generalized finite element method. Okay? That means that if you take any point in that domain, this holds. So the sum of functions is equal to 1. Okay, so now that we have the basis functions, yeah?
The approximate solution you get, is it summation from 1 to 5 or 1 to 6?
Ah, indeed. Thank you so much. Yeah. Thank you. Yeah.
The second line is the definition of phi I. X I plus 1 minus I divided by x I plus 1 minus x y, so it's 1. Or should first x be just x?
Sorry.
In the definition of phi,
Yeah.
the second line is 1. Just
The second shape function.
Ah, the second shape function is, yeah.
X, I guess.
Yeah, it's minus x, right? Okay, thank you so much. So now let's take a look. We already saw what the weak formulation is, but I want to approach arriving at the discrete equations in 2 different ways. Okay, so if we take only one element, of course you can express equilibrium locally to that element, right? And so if we do this, let's consider the equilibrium of one element. Of course, we're talking in a weak or variational sense, okay? So if you do that, well, if you remember the equation, xj, we had something that looked like this. Okay?
This is not this. This is a strong form, right?
Weak.
Weak?
This is a weak form, and you see that it is a weak form immediately. If you look, these here are the boundary terms.
Yeah.
Yeah, and also you see that the derivatives have been balanced.
Sorry, I was
Okay,
confusing strong.
no problem. So this is our local statement of equilibrium, or our weak equilibrium for that little element. Yeah. Now, if you take the shake functions, you saw that the shake functions are local, right? They are local to the elements they are behaving on, they are acting on. So if you look back at this figure, if you take phi3, well, phi3 is only going to be non-zero in E2 and E3. And this is also a very nice property of finite element, because at the end of the day, what you would expect is that if those functions are locally only, right, that the resulting system of equations that you're going to obtain is very sparse. And sparse system of equations are good. Okay, you can solve them fast. All right. So this is another nice property that does not happen if you take, for example, the Rayleigh-Ritz method, where you're not, suddenly, since your functions are acting globally, the system that you get is not sparse. Okay. So because in this element only phi I, phi j are non-zero, yeah, in that particular element we can actually express the displacement like this. All of the functions are zero, so it doesn't make sense that I write the expression, the full expression, taking into account all 6 shake functions. Okay, and these you can write in matrix form like this, where your phi is your element shake function vector, and your UE is your element degree of freedom vector. Now, if we're working with the Galerkin approach, we also have to express our weight function from the same way we express our trial solution. And these you can write like this as well. Just a dot product between vectors. Yeah. And I am following the notation that is commonly used in finite elements. So don't think about phi and u as being, for example, both column vectors or both row vectors. Okay? Think about them as being just vectors. And so when I write something that looks like this, I'm actually doing the dot product between those 2 vectors. And this is the way it is normally done in finite element literature. So if you do that and then you replace, because now I want to replace these, I want to replace them in the weak equation, right? What you get is EA B transpose B plus K phi transpose phi dx UE is equal to xi xj phi transpose B dx plus minus ni and j and then this is for all W. So let's see what happens. Well, first of all, of course, I need to define where this B transpose is just the derivative of the shape function vector with respect to x. But let's see what happens. All I did is I took this expression and this expression, right? And I plug this back here. So if I take the derivative of W with respect to x, so since whatever is a function of x is only the shape functions, right? The degree of freedom vector is just a constant, right? And since these are constants, basically I can take them out from the integral. And so you see that u shows up here and we shows up there. And now the statement before was that this equation on top was valid for all WH in that subspace, right? But that is no longer the case here, because the only unknown here is WE, because I know the shape functions. And so this statement has to be valid for all WE instead. Yeah? So that is all that happened between these two steps. I just take the trial solution, I take the weight function, and I am doing this in matrix form because it's easier. And then I plug that into the expression up, and then you see that the statement above becomes the statement below, where this is no longer valid for all WH in the subspace, but for all vector. It's a finite dimensional vector. Okay? And so if you take that equation and you see, well, if it has to be valid for all vectors, of course this is a vector of finite dimensional size, then what you get is that basically whatever is in the brackets has to be the same, right? So if you do that, then you get xj EA B transpose B plus K phi transpose phi dx UE is equal to phi transposed B dx plus minus Ni and J. And what you see here is that what you see on the left, this is going to be our local stiffness matrix, and this is going to be our local force vector. And it's expressed in matrix form. So if I have a 2 by 2, so you see that in that element, I basically have two shape functions that are non-zero, right? And so if you express this in matrix form, your B is going to be a 2 by 1, so B transpose B is going to be a 2 by 2. And already you know what's coming, because you have probably seen in other classes the stiffness matrix of your bar element being EA over L times 1 minus 1 minus 1, 1. Everybody has seen this at some point, assuming, of course, E and A are constant throughout the element. Yeah? And so our equation K E U E is equal to Fe is the local equilibrium of the element. Okay? Now, of course, you would expect that this doesn't say anything yet. We were just doing equilibrium in one element. So that doesn't take us to get the real behavior of the whole bar. But if you do the same in the contiguous element and so on, right? You get a bunch of expressions that are going to give you the local arrays for each element. So you have local stiffness matrices for all the elements, and then you have the local force vectors for all the elements. Okay, and so when you combine, and this combination is normally called assembly in finite element terminology. When you assemble all these local arrays into your full or global system of equations, right? Then you obtain the behavior globally. Now you see that, for example, in this right-hand side, there is one part that deals with the body force, this one here, but there is another part that deals with the boundaries, right? These are basically the forces that are acting at the boundaries, the actual loads at the boundaries. And so if you take the contiguous element, right, some of those forces are going to cancel or not until the end where you are actually applying the boundary conditions. So this is one way of approaching this whole finite element story, right? You subdivide the bar, you express the local equilibrium, and then somehow you describe the assembly of all these little components into the big picture. Yeah? And the missing part to finish this story is to define that assembly, because it's not sum, it's not a summation, it's a special type of sum. So you basically have to sum contributions that correspond to the right degrees of freedom. Okay? And this is called assembly. So the behavior of the entire bar is obtained by considering the contribution of all elements. This process is called assembly. So normally this is something that also you will find in many papers, defining A as the assembly operator, then your global stiffness matrix K is basically the assembly of all those little or smaller arrays, and the same happens with F, which is the assembly of all those force vectors. And now K and F are the global stiffness matrix and the global force vector. Then we are left with the system that we all know. K U is equal to F for U, which is basically the global vector of degrees of freedom in the system. Yeah. So let me just finish. I need a couple of more minutes because this K has nice properties, as I was discussing with a couple of your colleagues a few minutes ago. If you start with the Galerkin and it turns out that you conserve the symmetry throughout, what you find is that your K matrix is symmetric. And having a symmetric matrix, a sparse and symmetric, is something very nice because you can actually you can solve this very easily. So if your symmetric matrix, let's say you are using a direct solver to to get the solution vector u, then you can choose for a solver like Cholesky factorization if you're using a direct solver again, and then that is basically cutting half of the number of operations to get that solution vector. Normally, this is not really done. I guess most people go for iterative solvers because the requirement to get the solution goes from n cubed in a direct solver to something smaller, n squared. There are multi-grid solvers that are even lower that requirement, but we're not going to look at that at all in this class. Okay, but just to finish here, K is symmetric, positive, semi-definite. What does that mean? Who can tell me what semi-definite means? Positive semi-definite. Huh?
0 or high.
Yeah. So it has 0 or positive eigenvalues. And in this case, for this particular case of a bar, the unique 0 eigenvalue, we have only one, corresponds to what? Huh? Who has a guess? Well, I don't know you guys know, but anyone else? Can we solve this system? Well, you could say you could, but you need some tricks, right? But if you impose a boundary condition, then you can solve it. So your system is no longer singular. It does not have any more 0 eigenvalues, and then you can solve it. I'm not saying you cannot solve a system with 0 eigenvalues. Okay. I'm saying that if we prescribe the displacement somewhere, right, then our system is no longer singular, is positive definite, and then we can actually obtain a solution. So the 0 eigenvalue, what are we doing by prescribing this displacement somewhere along the bar? We are removing what?
The degree of freedom.
Indeed, we are removing a degree of freedom. But what are we doing to the bar? Yes, which means that we are removing rigid body motion. Yeah, that is the keyword that I wanted to get from you. Yeah. Rigid body translation. Of the bar. Of course, so far in this discussion, there is nothing regarding boundary conditions yet. So you would expect that something is going to happen. Let's say we fix these left nodes. Well, something is going to happen there because we said, if you remember, that we have to take functions from a space that has 0 value at that location, right? But we're going to talk that in the next class, as well as there is another nicer way, in my opinion, to arrive to the discrete equations. But this is finite elements now. Now we can solve a problem of a bar at least. So well, next class we will continue with this. We will look at isoparametric formulations in finite elements, and then we will go to higher dimensions and then to the heat equation, and that is basically going to be the summary or our review of the standard finite element method before jumping to p-FEM and to g-FEM and to d-FEM and to all these other formulations. All right.